record. Okay. So, yes. So we did start with some motivations, and we saw background in Euler's work, and so this was the start of analytic number theory, as we discussed already in 18th century. But now we are in 19th century, and the work of Dirichlet, that's kind of everything started in earnest, I would say. So we want to discuss this thing called Dirichlet characters. So they are also called modular characters. So what are they? So let's first of all fix an integer n bigger than or equal to 2. And then we consider the ring of integers modulo n, z over nz. This is ring of integers modulo n. And to any ring, you can attach a group, the group of invertible elements of the ring, right? So we consider the group of invertible elements here. So, and we call this group GM. So these are invertible elements of Z over MZ. Oh, NZ, sorry. So we know that a number modulo n is invertible in this ring if and only if it is relatively prime to n, right? So, of course, this Z over NZ, you can write it as by representative 0 bar, 1 bar. By this, I mean representatives of 0, 1, 2, all the way up to n minus 1 in this ring. And of course, then m bar, which is m mod n, so to speak, is invertible if and only if this m is, as I said, relatively prime to capital N, right? So immediately you see that the order of this group is Euler's phi function, right? So the order of GM, what is GM? This is GN, I'm sorry. Yeah, GN. The order of GN is phi n. And this is Euler's phi function or totient function. And this is basically the number of integers less than n, which is relatively prime to n. That's what it is, right? Okay, now, so this is a finite abelian group. And so by Dirichlet character to start with, we mean a character of this group in the usual sense. So fix a character. Chi from Gn to C star on Gn. Well, this is a finite abelian group. It's a finite abelian group. Sometimes it's cyclic, but it's not always cyclic. It's more complicated. It's a product of cyclic groups. And we know what the character means. It's just the multiplicative things to into C star. And fix one of those. Then what you can do, you can extend this almost brutally to the whole z over nz by declaring the value of character to be 0 on elements which are not relatively prime to, so extend chi actually to z by defining. So now we are saying chi of n is equal to 0 if n and n is different from 1, if they are not relatively prime to each other. And of course, chi of n is equal to the old chi of n if n and n is equal to 1. So now we extended this chi to the whole integers z, right? Then this has some nice properties. One property is that this is part of one of the assignments, maybe assignment 2, I think. I assign you to do this. That's very easy. It's just moment of thinking. First of all, this chi is fully multiplicative. Is fully multiplicative. In the sense that, as we define, chi of n m is equal to chi of n chi of m. This is for all n and m in Z. Well, you see, it's already multiplicative on Gn because it's a character, and I'm using the product rule on Gn, not addition. I'm just using multiplication. And you can see that when you extend, multiplicativity is going to be preserved by looking at, say, some cases. That's easy. And the second property is that this chi is actually periodic. Periodicity is that chi of, yeah, let me write it here. N plus n is equal to chi of n. So it has some period n, repeats itself after. I mean, that's because we defined it modulo capital N. So these things are called Dirichlet characters, either in the original incarnation as a character on Gn, or the way it's extended on Z, we call it Dirichlet characters. So these are, or modular characters. So this chi is, these are called, so put it this way, Dirichlet or modular characters. Okay. Yeah, yeah.
It's modular character theory, after the modular character theory. I'm thinking that's modular Ashken theory.
Oh,
Algebra.
right. So you mean representation theory in the positive characteristic case? That's called modular representation theory. Well, I mean, here there is I maybe, I'm not sure, but here, but both cases, they are like finite characteristic. Here is finite characteristic. That one also is a finite characteristic representation theory. Beyond that, I'm not sure. Yeah, I mean, I think, yeah, it could be, but it's a very general idea, and that's what we do. So let's look at some examples of this. Any other questions, by the way? So let's look at some examples. So example 1. Let's take, for example, n equal to 4. Then in this case, G4, order of G4. So the ring of integers modulo 4, there are only two invertible elements in it. There's 1 and there is 3. These are the only invertible. So the order of this guy is 2. And actually, this group G4 is cyclic group of order 2. That's clear. So there are only two characters as a result, because we know that cyclic groups, the characters of cyclic groups are basically, the dual group is isomorphic to the group itself. So this is going to be only two characters. So the only non-trivial character is, so actually you can work out the definition for it. It's just chi of n equal to, I mean, a formula for it, the definition we have, but there is a nice formula, -1 to the power epsilon n, where epsilon n is equal to n minus 1 over 2 mod 4, or mod 2, I'm sorry, which is equal to basically 0 if n is equal to 1 mod 4, and is 1 if n is equal to -1 mod 4. I mean, it's equal to 3 mod 4. -1 mod 4 means it's 3 mod 4. So that's our first character, Dirichlet character. We took n equal to 4, and we could have taken n equal to 3, and in that case, we would get a different character. So we can take now n equal to 8 for our other examples. Yeah, let's see. So let's take, so this is, let n be equal to 8. Now the group G8 has 4 elements. So you know groups of 4 elements, right? You know what are the groups of 4 elements? Sorry?
One of them is Z4, one of them is prime 4.
Yeah, exactly. One of them is Z4, cyclic group of order 4, obviously is always there. The other one is Klein's 4 group, which is Z2 cross Z2. And you know that this is from very, very basic group theory. First lecture, you know that they proved to you that these are the only groups of order 4, right? So in this case, this group has 4 elements as well. Now the question is, which one is it? Is it cyclic group of order 4, or is it Z2 cross Z2? Which one is it? Yeah.
I think it's the second.
Not everything is multiplicative. What do you mean? Yeah, not everything is a unit. That's right. But does it mean that it's not? Does it follow that as a result? I mean, is the proof? Yeah. So any element here is order 2. Yeah, but why? You see that? Yeah. So the things are, yeah. So the things that are invertible modulo 8 are 1, 3, 5, and 7. So then why all those elements have order 2 then? Is it clear? Yeah, 3 has order 2. Yeah, 5 has order 2, and 7 has order 2. Yeah, every element has order 2, so it means that it's Z2 cross Z2. Right. So that's Klein 4. You said that, right? Okay. So G8 is Z2 cross Z2. I don't need it, but I just did that. So is equal to 4. So the characters, so there are 3 non-trivial characters. So why there are only 3 non-trivial characters? Yeah, but there is something to just think about something much simpler even. Why am I saying there are only 3 characters? Yeah.
There are exactly.
Yeah, because we proved in the last lecture that there are exactly 4 characters. The number of characters is actually equal to the number of elements in the group, and actually structure of the dual group is isomorphic, non-canonically to the group itself. So there are only 4 characters. One of them is the trivial one, so there should be 3 non-trivial characters. Okay, so 3 non-trivial characters. That's good. So these are the ones, n to minus 1 to the epsilon n. See, the epsilon is the one that I introduced over there. Okay, the other one is n to minus 1 to wn. And the last one is the product of the 2 minus 1 to wn plus epsilon n, where wn is equal to n squared minus 1 over 8 modulo 2 again, which is equal to, comes out 0 if n is equal to plus minus 1 mod 8, and equal to 1 if n is equal to plus minus 5 mod 8. Now, these 3 statements are not obvious. Someone has worked out these formulas, so you have to check the formulas. I'm not saying that you should be able to see it on the spot, right? Just right away. These are some formulas that someone has labored and has found these formulas. We have the definitions. We can write all of them, but in terms of these epsilon and w, it takes some work to check that they match. The 2 sides match, basically. Okay, so that's our second example of Dirichlet characters. Okay, so let's look at another example where actually Gn is going to be a cyclic group of order n minus 1. So that's another example. Any question about this, by the way? No, it's just a verification we have to do, but that's okay. Okay. So now in this case, let n be a prime. So we look at the case of prime, and then, of course, in this case, z over nz is a field. If n is a prime, I mean, this is a field if and only if n is a prime. We know that, right? Now, in this case, what is the structure of this group? What kind of group is that? It's exactly. So we know that in any field, any finite subgroup of any field is actually cyclic. You know that famous theorem. So this is a cyclic group of order n minus 1. So there's going to be exactly n minus 1 characters. And there is only one character whose square is 1. So let me write it down. So this character is very important in number theory. And so there exists unique character whose square is 1. So there's a question in your assignments. I ask you to prove this. Again, this is quite elementary, but it's good to try to prove it. So I just ask why. I'm saying it's not totally obvious. It's given by chi of n is equal to okay. So in terms of symbol, there's a famous symbol. You remember? Have you seen this symbol in number theory or elementary number theory? Maybe you have taken. It's called Legendre symbol. So this is n p. This is called Legendre, because Legendre introduced this Legendre symbol, which is equal to 1 if n is a quadratic residue mod p. I say it like this: if n equal to quadratic residue mod p, and minus 1 if n is not a quadratic residue mod p. If n is not a quadratic residue mod p again. So what does this mean? It means that depending on n, we are looking at an equation, at the simplest type of nonlinear equation, quadratic equation. So the equation we are looking at is the following equation: x2 minus n equal to 0. So we are saying if this equation has a solution in fp, yeah. So of course, I mean, this p is our n. Remember, we are in this case, but it's always a good idea when it's prime to call it p. So if it has a solution, then I mean, this n basically, then we know that the value is 1, and this value is related to the number of solutions here. It's actually its number of solutions minus 1, right? Is number of solutions minus 1. For this, I have to assume that n is a odd prime. So n is not 2. That's important. So capital N is an odd prime. So I exclude the case of 2 because 2 is an exceptional case, and I don't want to. So there are exactly, if there is one solution in this case, you can make sure that there is another solution. It's negative, basically. Negative in this ring. And then there are 2 solutions, so you take number of solutions minus 1. And then in the other case, when there are no solutions, well, number of solutions, again, minus 1. So this is 1, this is minus 1. Because there are no solutions. And do you know for how many of the elements in here, for which ends there are, how many ends there are solutions, and for which end, for how many ends there are no solutions? Do you know that? So you have to use the fact that this group is a cyclic group. So you can write everything as powers of something. And for an element to be a square, that power has to be even. So half of those powers are even, and half of those are odd. They are not quadratic residues. So half of the elements are quadratic residues, and half of the elements are non-residues. So this is very easy to understand. But what is not easy is to know which one is residue, which one is not residue, because it depends on finding a generator of the cyclic group that generates this, and that's a very hard question. But that's another issue. Anyhow, so this is a Dirichlet character now. I mean, this chi, which is Legendre symbol, and choose P. That's the only non-trivial character that squares to 1. It's a real one. So its value is either +1 or -1. So if you have a character, Dirichlet character or modular character, whose square is 1, you're sure that its value is either 1 or -1. Why? Okay, think about in general terms. You have a character, a Dirichlet character, whose square is 1. I'm saying it either takes value 1 or -1, and nothing else. Why? So that's the case. But in general, can you tell me the argument? What is the general argument? I'm asking a very general question now, right? If you have a character whose square is 1, I'm saying either takes value 1 or -1, nothing else. Yeah. Those are the only two numbers whose square is 1. That's true. That's the answer. I was thinking of a more difficult answer. You found even simpler answer. I was going to relate it to some facts that it takes only values on the circle and but that's irrelevant. Yeah. Very good. Any other questions or comments? Okay, so we have these Dirichlet characters. Now we are going to define some functions. It's called Dirichlet L series or Dirichlet L-functions using these things. So these are some generalizations of Riemann zeta functions. Oh, by the way, maybe before we move on, I tell you something. I ask you a question. So this group Gn, does it ring a bell for you? I mean, is it, have you seen this group before in some other context? In which context? Huh? Field theory, yeah. So how this group appeared in field theory? Sorry? Yeah, it is the Galois group of an equation, which is xn minus 1 equal to 0. So, and that extension field that solves that equation is called cyclotomic extension. So this is the Galois group of cyclotomic field over Q. So let me write it down because this is very important. So this is equal to Galois of Q Cn over Q, where Q Cn is a splitting field of xn minus 1 equal to 0. Okay? So this is the smallest subfield of complex numbers that contains all the roots. Okay, so what is Cn, by the way? That's equal to e to the 2 pi I over n, for example. So why that's the case? Why this is the Galois group of these things? Okay, so you know that if you have an automorphism here, if you have automorphism phi from Q Cn to Q Cn, and automorphism over Q, right? It should send these roots to roots. So there are n roots on the circle, right? I mean, there is one always there, and then there is Cn, and there is Cn squared, and so on, are nicely located on the circle. So it should send roots to roots, that much we know. But because it's an automorphism, it should send primitive roots to primitive roots. It cannot send a generator to non-generator. It would miss something, right? So Cn that I wrote is a primitive root. So it should send this Cn into primitive root. So other roots are Cn to the power k. So this root is primitive. If and only if when. What kind of condition you need in this power k? K is relatively prime to n, right? Okay, so there are exactly this many primitive roots. So this phi k sends Cn to Cn k, okay? For different powers k, well, k and n. is equal to 1. And if you study the multiplication rule of this thing, which is in the Galois group, so you say phi k prime is equal to phi kk prime. Mod, of course, kk prime is done mod capital N, right? So this means that these two groups are exactly isomorphic. The Galois group of this and the group of units modulo N, right? Galois of QCN. Cyclotomic field of order N over Q is isomorphic to Gn. Now, this is a very important fact. I mean, you will see that actually what we are doing here, we are attaching a function, an analytic function, to a representation of a Galois group very soon. And of course, it's very rare for a polynomial equation to have abelian Galois groups, okay? And the question was how to attach these L-functions to non-abelian extensions, non-abelian polynomials. And that was where Artin's L-functions come into the game. Instead of Dirichlet L-functions, Artin's L-functions. That's 20th century now. So this will, so some of you I assigned to do Artin L-function. Yeah. So this is the first clue why they are important. So that's okay. You haven't seen. I mean, I'm just scratching the surface here, but that's you'll see. Okay. So now to do things, we need to go back to analysis a little bit. So this is some theorems from complex analysis. By the way, any question about this? Okay. So the first theorem we need is the following. Let Fn from U to C, yeah. So this is a sequence of holomorphic functions. Such that they converge uniformly on compact subsets of U, such that Fn converges to F uniformly on compact subsets of U. You know the meaning of these terms, right? Uniformly on compact subsets. So for any compact subset K of U, the sequence uniformly converges to F. Fn is given, F is also given. Now the claim is that this F again is holomorphic. Then F is holomorphic. And also the sequence of derivatives converges to the derivative of F. And Fn prime converges to F as n goes to infinity. Oh, this is called normally? Oh, is it called normal? Uniformly on compact? Oh, I see. Maybe because of normal families in complex analysis or something. Like, yeah, right. So you can convince yourself by giving counterexamples that these two conditions are necessary in order for the conclusion to be true. But that's okay. But the proof is something we have to use a strong tool, which is Cauchy's integral formula. Okay, this is Cauchy integral formula. So basically, it says that for any z0, if you take a simple closed curve counterclockwise oriented around this Z0, completely inside U. Yeah. In this situation, you can always write the value of f at any other point in terms of the counter integral value on the boundary C. So then Fn of, say, Z0 is given by counter integral, which is 1 over 2 pi I, integral over C, Fn of Z over Z minus Z0. This is dz. Yeah. Okay, now we can take limit. Because these Fn's converge uniformly on compact subsets, so you can take a compact subset that contains this contour and interior, and then you're on that contour compact set, and you see that this integral converges to the corresponding integral in terms of the limit, which is this one. So then take the limit, and then you conclude that f of Z0 actually is equal to 1 over 2 pi I integral f of Z minus Z0 dz over C for all points Z0. Now, any function that's defined like this is automatically holomorphic, because it doesn't matter what this f is, because 1 over Z minus Z0 is a holomorphic function in Z0. This is just a fraction, very simple. And you're integrating those things, so that's just... So such functions are holomorphic. So yeah, this Cauchy integral formula is like if and only. If you have some function that has an integral representation like that, it's holomorphic. And if it is holomorphic, then it has that kind of integral representation. Okay, so for derivative, just take derivative of this. Use other Cauchy integral formula. For derivative, use, I mean, we have a corresponding formula also for Fn prime of Z0. What is the formula? Is it 1 over 2 pi I squared, or is it a squared, or no? Only Z minus Z naught squared, right? Yeah, you can almost differentiate this here. Squared Z over C. And then you use the same argument. So that's very good. So, no, I don't see any change in sign here. Oh, you differentiated?
Yeah.
Oh, yeah. I differentiate with respect to Z0. So what is that? That takes care of it. The derivative of minus 1 over Z is, yeah, that's what it is. So this is one result that enables us to prove that a lot of these L functions or zeta functions and all these things, again, are holomorphic. So that's really like a basic result. It's like a power horse for us, a really working horse. It just proves a lot of functions that we need to be holomorphic are holomorphic. Without this, we wouldn't be able to do that. Second result is a result of, again, basic calculus, but maybe it's not done usually in calculus, but can be done, or combinatorics. So the second one is a lemma. This is amazingly deep, but once you're told what to prove, you can prove it, but discovering it was quite something. This is due to Abel. So let AN and BN these sequences. So let A and P be equal to sum of AN. These are sums of N from M to P, and SMM prime is sum AN, EN, and from M to M prime. Okay, then SMM prime, you can write it as sum n from M to M prime minus 1, AMN, Bn minus Bn plus 1, I believe, plus AM M prime. And then there is EM prime. Okay, so proof is elementary. You can, you're told what to do, what to prove, then you can prove it. So proof, this is, I leave it as an exercise. Maybe I assigned it, I'm not sure. You'll find it in assignment 2 maybe. But what kind of result of calculus this reminds you? I'm saying this is a discrete version of a result, famous result, one of the most fundamental results of calculus. It's integration by parts, yeah. If you interpret summations as integral from this limit to that limit, and then you see that this is a discrete version of integration by parts. So integral A to B, F, what was integration by parts? F G prime dx, right? Is equal to integral Fg from A to B minus integral F prime G. Yes, let me just check. Yeah, this is the, yeah, which is, yeah, that's what it is. It's a consequence of two things, right? What two things? Product rule for derivatives and fundamental theorem of calculus. Putting the two things together gives you this magic formula, this one. And this is the discrete version of that. Okay, so, but this has amazing applications for what we are going to do. Without this, nothing would work. Any questions? So we need one more fact from analysis, which is an inequality. Yeah, so this is, as I said, all these things are quite important to prove things. Okay, so there's another lemma. So let alpha be less than beta, bigger than 0, z equal to x plus iy, and x is positive. Then we know that then the statement is that absolute value of e to the minus alpha z minus e to the minus beta z is less than equal to absolute value of z over x. Well, x is positive anyhow, doesn't matter. That's e to the minus alpha x minus e to the minus beta x. Yeah, that's an inequality. So the proof, the only thing that you have to use is how to write this as an integral again. So basically, you have to notice that e to the minus alpha z minus e to the minus eta z is equal to z. Just write it as an integral alpha to beta e to the minus tz dt. It's just this integral. Okay, so then absolute value e to the minus alpha, we want to estimate that, right? Minus beta z is this less than or equal to absolute value of z, integral alpha to beta. And then I've got e to the minus tx dt. You see, you pull this absolute value sign inside. And what is absolute value of e to the minus tz? Well, t is a real parameter, and z is x plus iy. E to the iy is just a phase, disappears under absolute value. What remains is e to the minus tx, and that's this one. And then you just replace, you integrate that, you get this. Okay, so that's so let me not write it, but you know what. Good. So that's that. Now we're ready to define some very general class of functions called Dirichlet series. Beyond L-functions, Dirichlet series is a very, very general class of analytic functions. That's kind of hallmark of analytic number theory. So these are Dirichlet series. Any questions? Okay, so let's go into Dirichlet series then. Okay, so you have to fix two pieces of data. First of all, sequence lambda 1 less than or equal to lambda 2, lambda 3. And the sequence is going to infinity, is non-negative. And the sequence an from an belongs to C. So you have two sets of data in order to define your function. First of all, there's a sequence of non-negative real numbers. They approach to infinity, they're ordered. And then there is just a random sequence of complex numbers, whatever you want, and from 1 to infinity. The associated Dirichlet series is sigma an e to the minus lambda n z over n. This is a class of functions that is as important as Taylor series. I mean, it's a huge class, and they are much better for number theory than Taylor series. So we'll see gradually. You can think of it also as a generating function, generating series, because you're kind of encoding the sequences of an and sequences of lambda and into, you're packaging it into. So it contains information about both in a kind of slick way. But yeah, but how this came about, it's a long story, and that's we have to gradually grasp this. So examples of this are if lambda n is equal to log n, then you get sigma an over n to the z. So this is what most people call Dirichlet series, actually. But this is a special case of more general Dirichlet series that Serre defines in the book. So this is This is what most people see as the Dirichlet series. And in fact, I hate to write it as n to the z, but I would write n to the s. But that's what people write now. Okay, so the second case would be lambda n equal to n, then you get this series sigma an e to the minus z to the power n. So this is like almost like a power series composed with function e to the minus z. You have a power series composed with this function e to the minus z. Now, the question that's relevant is to understand where this series is convergent, the domain of convergence of the series. That's the most important question. So the question is where star is convergent. So in other words, what is the biggest set, possible set, that the series, the Dirichlet series, a star, given like that, is convergent? In general, what can we say about it? That's the question. So to give you some idea, I would say, let's think about a power, for example, power series that you learn in complex analysis, right? So this power series. The power series are kind of nice because its domain of convergence is there is a radius of convergence, there's a disk, right? So there's a radius of convergence rho. In the interior, right? This guy converges absolutely. And it's a holomorphic function there. It's differentiable. This is what you prove in complex analysis by basic estimates. And outside, at no point outside the disk is convergent at all. At no point is convergent. On the disk, anything can happen. Can be convergent at some points on the disk, can be divergent, and there are on the disk. So there is a number rho, it's called radius of convergence, that you can actually write down. There's a formula for rho in terms of ANs, you know, even that you can work it out, and you know that this is just, so this rho is radius of convergence. Now, rho is bigger than or equal to 0, less than or equal to infinity. When we say rho is infinity, it means that it's convergent everywhere. The disk is infinite everywhere. So then in that case, it's an entire function, right? So we want to find something like this for this series. And I mean, this case is much harder to understand the nature of domain of convergence of this series. So that's why we need those 2-3 lemmas that we proved in order to get some understanding of domain of convergence of these things. So, right. So now let me write the main theorem here. Yeah. So this is the theorem. Assume sigma an e to the minus lambda and z is convergent or converges for z equal to z0. Then it is convergent uniformly on any domain of the form So let me draw its picture first, and then what is that domain of the form absolute value of z minus z0, real part of z minus z0 bigger than or equal to 0, and argument of z minus z0 less than or equal to alpha less than pi over 2. So the domain that we are looking at is here. Okay. It contains these two lines all the way up to z0. It's convergent at z0, we assume. And it is uniformly convergent there. Now, this alpha could be anything for less than pi over 2. So what does it mean? It means that you can actually have this also, that, but not the line. The line is, you cannot say anything about the line, the straight line, the dashed line. But any opening is okay. That's what we can say so far and what we want to prove. So it's clear what the thing says, right? So, and that's really very nice. So we have convergence only at one point. Now we have convergence at infinite number of points and of this nature. So again, you should compare this to this result. So what does this result here? It says that if you have convergence at some point, then you have convergence at any other point that's in the interior of the disk that's with that radius. That's how you prove such results, right? That's you come about this rule by proving that if it is convergent at some z0, it is convergent for all z whose absolute value is less than z0. And this is the analog of that result for the case of the Dirichlet series. So let's see how the proof goes. Without loss of generality, WLOG, we can assume that Z0 is 0. We can assume Z0 is equal to 0. I mean, you can just shift and translate. That doesn't affect anything. So we can just assume that. So then, want to show that so this function, that the series is convergent for all z such that real part of z, first of all, is positive, because the point that we have here now is at the origin, for all points whose real part is positive, and it's located inside a wedge of arbitrarily large but less than pi over 2. And that wedge you can describe as absolute value of z over real part of z less than or equal to k. So this is a parameter which is bigger than 0. For some k. Or you can describe it like the way we describe it over there. All right. So then the rest is an application of Abel's trick. So in other words, discrete some integration by part. So now let epsilon be positive. Since some an converges, So why this sum an converges? Yeah.
That's by hypothesis.
By hypothesis, I'm assuming Z0 is 0. So it's convergent at Z0, means it's convergent at 0. If you put 0, you get some an is convergent. Okay, so that's clear. So since sequence an converges, there exists n such that for all m and n prime, bigger than or equal to n, absolute value of a m and n prime, sorry, is less than or equal to epsilon. I mean, this is you just say that if you go forward and then take any chunk of the tail, it's going to be small in absolute value. That's follows from convergence. Fixing epsilon, there's always such capital N such that this holds. So apply Abel's lemma. Then we get Smn prime is equal to some m to m prime minus 1 amn e to the minus lambda n z minus e to the minus lambda n plus 1 z plus a mn prime rather e to the minus lambda n prime z. Yeah. Right. So now let z be equal to x plus iy in the domain. So we just pick now a point here that's satisfy the condition for z0 equal to 0. And apply our inequality. We had an inequality, right? Last thing we proved. If you apply this to if you apply inequality to these terms in the interior, you get the following estimate. You get that absolute value of M prime, okay, is equal to epsilon times 1 plus absolute value of z over x. I believe I should say less than equal to, yes, less than equal to times 1 plus, sigma m to prime minus 1 e to the minus lambda nx minus e to the minus lambda n plus 1x. Yeah, and okay, so n goes from m to m prime. That's what it means here. So that is absolute value of S m prime is less than equal to epsilon. Now, these some telescopes. You see, they cancel each other. 2 by 2 only first and last term remains, right? So then we get this is less than equal to epsilon times 1 plus k times e to the lambda x, lambda mx, first one, minus lambda mx, minus e to the minus lambda m prime x. Okay, so then this is less than equal to epsilon 1 plus, and this thing is because x is real, this is less than or equal to 2. Oh, this one? Where it comes from? M prime plus 1? Oh, this is M prime, first of all. I should have. There should be, the last time should be M prime. Oh, here. Oh, this is N plus 1. Yes. So this one should be. Here? Oh, here. What should be, you think? Oh, according to my formula in general. Oh, yeah. But it's less than or equal to 2 anyhow. Anyhow, so I call that again K prime, so less than K prime. It's a constant, which is independent of X and all that. So yeah, this shows that the series is Cauchy. So it's convergent. So because for any epsilon, it proved that there exists an n such that the difference between mth summation and m prime summation is less than or equal to epsilon if m and m prime are far away from the starting point. That's Cauchy. So Cauchy, hence convergent. Okay, so that's the one of the main things we wanted to achieve. So let's look at it again. So any question about the proof? Yeah, the proof is technical and is not fun. I agree. I mean, it's one of those results that perhaps several generations worked and they found this is slick proof. I mean, I'm not sure this is I have actually studied, looked at, I should say, Dirichlet's paper is far more complicated, but he's using this sort of tricks, Abel summation. Not Abel summation, I mean, this Abel's formula, but he's always working with real numbers, not complex numbers. So this is completely inside the reals, not complex. So I don't know if it helps or not. Maybe helps, but some regards it doesn't, because complex analysis is much more powerful than real analysis. Complex analysis is the real deal, right? All right, so now what we want to do, yes.
So the parameter alpha for the spread, is there a limit formula for it, like basic conditions? We know anything about how to calculate alpha?
Oh, the alpha is arbitrary as long as it's less than pi over 2. The opening can be as big as you want unless any alpha, but it should be less than pi over 2.
Okay, the alpha is from the series.
Oh, no. That alpha is anything you want. But in order to prove uniform convergence, you need to fix. The claim is that it's not uniform over the whole thing. You see, okay, so actually, no, this is a very good point you raised. So let me mention this, and then I mean, a corollary that we want to get is important, is relevant to your question. Yes. So the way that the corollary goes that, so this is corollary 1. If a Dirichlet series converges, so here is if a Dirichlet series converges for z equal to z0, right? Then it converges for real part of z bigger than a real part of z0. And the limit is holomorphic. Now we are not using any alpha, and now we just throw away alpha because it was a nuisance. It just needed as a device to prove the uniformity and all that, but now we just throw it away, but we can just write a cleaner statement like this. Then it converges for real part of z bigger than real part of z0, and the limit is holomorphic where? In real part of z bigger than real part of z0. So let's see what does the result say. The result says that if you have a Dirichlet series that's convergent at some z0, draw this line, then it is convergent in the right half plane defined by that z0, and it's holomorphic there. And we should forget about the line itself because we cannot make any statement about the line. Question?
That was
Exactly.
that's what was. And we're fixing the alphas from the other.
Yeah. No, I mean, so we are, in fact, it's better than compact subset. Is actually uniform on subsets which are like of that form. And why we needed that? Because we needed it in order to use the first theorem that I proved to make sure that the limit is holomorphic. So both things now come into the game. It's conversion everywhere for real part of it, and it is holomorphic there. So yeah, alpha was a device to get us into this holomorphicity, and this is kind of typical in complex analysis. These wedges, these angles, like in the Stokes phenomena, these things, they're always like they're like just like that. Okay, so what we have to pay attention is this right half plane. So that's why in all analytic number theory, spectral geometry, you hear right half plane, right half plane, right half plane, right half plane. It's always right. It's because of this result. Second thing is that there is a best abscissa of convergent. So okay, so this is something that says that, okay, if it is convergent here, then it is convergent in the right half plane and it's holomorphic there. But now we want to say that we can push it to a maximum limit so that get the biggest domain of convergence. And the biggest domain of convergence, again, is going to be of this form. Well, that's obvious because of the thing we proved. So this is corollary 1. Now corollary 2 is that the set of convergence of F, convergence points, I mean, F is really a Dirichlet series. Always contains, okay, so contains a maximal open half plane real part of Z bigger than rho. So eventually then we reach a number rho such that rho, a number which is real, it doesn't have to be positive, it could be negative, that's okay, such that the Dirichlet series converges there, and certainly does not converge at any point with abscissa less than rho, and on the line rho, real part equal to rho, anything can happen. Can be convergent, can be divergent, this sort of. This also follows from what we proved. If you think about it, it just follows from that. Because if it is convergent at some other point, it's going to be convergent everywhere, and so this is not the maximal, and da da da.
Have a line.
Exactly, a line of, so that's now we have a much better understanding of the domain of convergence. So it's comparable to complex to Taylor series, Power series, but there's going to be a surprise. There's a surprise on the way. So these things are more complicated than Power series, in the sense that there is another number rho prime, where if real part of Z is bigger than rho prime, it is absolutely convergent there, but less than rho prime is not absolutely convergent, it's only convergent. But this didn't happen for Power series, you see. For Power series, there was this radius, less than that is absolutely convergent, bigger than that is not convergent at all. But this doesn't happen for, but this is more complicated here. So now, so let me write it down then. So as far as absolute convergence goes, there exists another, in general, a different number, rho prime bigger than or equal to rho, such that f of z is absolutely convergent for real part of z bigger than rho prime, and is not absolutely convergent for real part of z less than rho prime, and not absolutely convergent for real part of z less than rho prime. And obviously, this rho prime has to be bigger than rho, because if something is absolutely convergent, it's of course convergent, not vice versa. So then the setting is that it looks like there are two walls, not one wall. There are two walls. So this is the picture we should have in mind now, in general. This is rho prime. This is rho. Here is a very complicated word. Not absolutely convergent, but convergent. It can happen. It can happen that rho is equal to rho prime. That's possible. But in general, we have to allow that, and we'll see that in a second. As we come back, I'll give you the examples. I think once you see the examples, you see that, okay, so yeah, this makes sense. This is rho prime, rho. Rho prime is bigger than or equal to rho. That's the deal. So I think it's a good time to stop. If you have questions, feel free to ask. I have a low battery, only 5%. My God. Oh, so pause.